So this is our topic. That was magical. Well, this is a nice diagram that sort of outlines the process in general. There's an intense laser beam, typically a few to 50 or so cycles, femtoseconds, I should say. Okay. The most common one up to now has been a Thai sapphire at 800 nanometers. It's focused into a gas, a collection of gas, inert atoms, neon, helium, argon, things like that. And without an explanation, you focus this laser in this short pulse to a high intensity, not quite enough, not with an electric field high enough to just rip electrons off, not having an electric field as strong as the binding energy of the outer electrons, but a fifth of that or a tenth of that. So some relatively high electric field comes in to this group of inert atoms, and what comes out is this spectrum of harmonics, a comb of harmonics. So if 800 nanometers is the fundamental, these are 800 divided by 65, 75, etc. So it takes radiation at 800 nanometers and it gets you into the region of 9.5 nanometers. This is an angstrom, so a tenth of this, so down to 10. And they're always odd harmonics, or not always, but it's the most common thing. If you want to get even harmonics, you have to do something special. So the way this works, so we're going to go through and see if we can understand why we get all these odd harmonics and why we get such high photon energies, and which are necessarily very short pulses. They started with very short laser pulses, and they can be really quite, it's the only mechanism we have to regularly get into the attosecond region, producing pulses that can probe with way under a femtosecond. So the FELs have had a few special papers that show they could get sub-femtosecond, half a femtosecond, a third of a femtosecond, but it's not their usual operation. And this is the usual operation. So we're going to try and understand this. The focused radiation is sort of reddish at 800 nanometers. And it's shown here going through the gas and then expanding, but along with it is coming this sort of ultraviolet looking radiation. Goes through a filter to block the IR, the infrared, from the laser itself, and just let the EUV come onto a grating. Grating disperses it, spreads it on a CCD detector, which you view on your screen. So that's the overall idea. This is from KAIST in Korea, from Changhi Nam. And here are some of the equations. We're going to, a little bit of an explanation, a first look at it, but with some equations. And we'll have to go over these a little bit right from the beginning. This is a good page to keep this information at hand. And don't forget, by the way, posted at the class website is this list of formulas. And I'm sure all of these formulas are there. Maybe a little bit more, probably a little bit more, maybe not. Here's what I was looking for. Well, there is a little bit more, yeah. The relationship between for what intensity, what electric field do you get? Okay, that's really important in this field, and I guess I haven't quite put it here yet, but it is on that. We'll see it. We'll see those equations in a moment, but for a convenient place for all the formulas, I would look at that, the B course site, and just look for the file that says something like equations. Anyway, here's the idea. An infrared wavelength comes along of 800 nanometers, the curvature of the wavefront to show focusing. It's brought down to focus on an area much larger than a single atom. So things are not to scale here. And in fact, what happens is the electric field of the incident radiation is sufficiently strong to pull an electron from an outer an outer orbital, okay? And then once it's out, it actually tunnels out because the electric field, again, is not quite as strong enough to easily pull it out and a couple of its neighbors. So it's tunneling, it's chosen, the intensity is chosen to give an electric field which is a little bit less than the binding energy. And then once that electron is pulled out, which happens in a very short time, then the electron is in the laser field, the strong laser field, and it gets accelerated away from the atom when, as the passing wave goes through its cycle, the electric field turns around, and it probably turns around here and starts slowing down the electron. Finally, the electron reaches the furthest distance away, and then the electric field is still pulling it back. It's reversed, and the electron comes back towards the atom. This distance is kind of long, and the atom is kind of short, so the electron does not always recombine with the parent ion, but when it does, it brings a lot of energy that it picked up when it was free in the laser field. It brings back a lot of that energy, plus whatever binding energy it had when it left. And that combination, this thing comes crashing in. You can imagine that's quite a deceleration, and photons are squirted out. And here's our photon, which I call EUV. Most people in the high harmonic community call the same region. We all call it extreme ultraviolet, but they'll call it XUV. And I'm partially guilty for that because many years ago I formed an optical society, what they call technical group, and I also called it XUV. But I learned later that just for what's going on in the names, that the astronomers called extreme ultraviolet EUV. And lithography calls it now EUV because of the astronomers, actually, directly because of them. So you'll just have to recognize XUV and EUV. So, here's something about the tunneling. Let's look at the scale first. This is the IR wavelength, the electron path, that's this thing, and the neon atom. What's the ratio of these three things? It's 800 nanometers here, a path length of 4 nanometers in one direction, and the size of an atom, an angstrom roughly, or 2 angstroms, okay, in diameter. So that's the scale of things.
Professor?
Yeah.
I have a question.
Yeah.
So after the electron recombines with the atom and it generates the EUV,
yeah.
At that instance, there is still the IR laser coming in, right?
It's still coming in, so the process continues, yes. And
okay.
So that, that atom could possibly also generate other photons.
Okay, so it's like so basically we get like a whole flux of both the incoming radiation as well as the EUV coming out.
Yeah, so let's pay attention to that later when we look at some of the time scales for this and how long is the laser pulse. The laser pulse is often many femtoseconds, a few tens of femtoseconds, 50 femtoseconds. So that would be a very long time to have the process repeat, okay? Sometimes it's only one cycle, which is roughly, what is it? Less than 3 femtoseconds is a full cycle, okay? Here it is. What is one cycle at 800 nanometers? It's 1/3 of a femtosecond, so a little under 3 femtoseconds, right? So it could be short, but it could be long, okay? So let's look at some of the equations that we're going to wind up, we're going to wind up looking at. One is, what is the maximum photon energy that can come out of here? Well, early on, without quite understanding it, people found that the maximum photon energy was this numerical factor. Initially, they just wrote 3.2, but And then a theoretical understanding came along, which is not too complicated. We're going to do it. And you'll see this number come up. 3.17 times this U sub p. And it's just a measure. U sub p is an unfortunate name, but it corresponds to the average kinetic energy of an electron, okay, in a cycle. And this is the ionization potential. So combined, we'll see that these factors can be written in the following way. This is this average kinetic energy will depend on the intensity for sure, and it also depends on the wavelength squared, all things that we'll see. And numerically, this is what it looks like. So this is saying, excuse me, so 9.3 times 10 to the minus 14 times the intensity in units of watts per centimeter squared and lambda squared in units of microns, okay? So these are formulas we're going to see shortly. And what do I want to say? Well, I'll come back to it. And these are just some units that matter here. This is just from the Bohr atom. So these are all probably from the text, but the Bohr radius for the n=1 radius for a hydrogen atom, which is known universally as A sub 0, and this is the value, 0.529 angstroms. And I called it here also A sub B for Bohr because we have several other things and they relate to the Bohr the Bohr model of the hydrogen atom. And this time, this is the circulation time for an electron to go to make a full cycle. It's 152 attosecond. Sometimes you'll see that the natural constant this is like a diameter. It's basically the circumference divided by the speed of the electron, but that's what's happening here. But sometimes you'll see it without the 2 pi. This would be a radius and a circumference, right? And sometimes so you'll see it as something 152 divided by 6, whatever that is. So something like 30 attoseconds, and they'll call that the atomic scale time. But at any rate, I tend to use the circulation time, 1 orbit. And this is the Bohr field, the electric field, just calculated for an electron at a distance of the Bohr radius from a nucleus of 1 proton. And if you calculate that, that's 51 volts per angstrom. And watch out because sometimes I'll put it in volts per nanometer. Okay. A critical intensity would be the intensity associated with the square of that field. And that comes out to, as you see, 3.5 times 10 to the 16. Basically, we're never going to work, the high harmonic people never work at that high intensity because it would not only take off 1 electron from the outside, from the outer orbit, it would take off many electrons, too many electrons, and it will screw up the process in a way we'll learn about later. We wind up creating a plasma. And what we want is an interaction between lasers and lots of atoms, collectively many atoms, but we don't want too much of a plasma. So we want those, and there will be a lot of free electrons because I think I didn't quite say it, I was getting there. But after this electron goes this distance, a few nanometers from the parent ion and comes back, it doesn't always hit it. There's a divergence here of this radiation, and it's somewhat of a quantum calculation of an electron wavefront going away. But at any rate, you can just imagine that the electron doesn't necessarily recombine with the ion. And in fact, the efficiency of recombination really lowers the amount of power we can get out of high harmonic. So tricks to get more out are always of interest, but it's this lack of recombination, missing it, leaves electrons, a bunch of free electrons, which is a plasma, and we don't want too much of that. So we try to keep the intensity of the laser low enough, well below this, so that we're not pulling off too many electrons. So a typical operating point would be like 3 times 10 to the 14th watts per centimeter squared, 100 times less in intensity, so 10 times less in electric field. And then these are things you know about for bandwidth limited pulses. What kind of bandwidth in photon energy goes with what kind of time duration, both full width, half max, okay? Okay.
Atwood?
Yeah.
So you've listed out a lot of values for the Bohr atom, and I know
Yeah.
the Bohr atom is like a good starting point for lots of models, but what I don't, the tau for the Bohr atom, like the amount of time that it takes supposedly for an electron to circle.
Yeah.
Why would that be of any use, since we know that electrons really don't, you know,
Right.
circle the atom in that way?
Yeah, no, these are really good questions. Just that the Bohr atom and is just such a perfect model and gives us some kind of natural time scales, but with other atoms, which are more likely what we're going to use, neon, argon, etc. This is not the time scales that we're going to see, but it is just to give us a benchmark of, you know, how big is an atom. Again, this changes for higher Z, and what kind of time scales are natural time scales. So, and what kind of electric fields might we be working with? It's just to give us some basic, easily available information to scale things with. But in the end, we're going to move right past all this. Okay. So good observation. Thanks.
Professor?
Yeah.
I had a related question to that tau B, actually. So you said,
yeah,
you said earlier that the process, like during the process, once electron gets kicked out from by the radiation, it gets accelerated by the laser, and it comes back.
Yeah.
So then I was wondering how come like the time that it takes for electron to come back doesn't depend on the laser intensity or the laser wavelength in that equation?
Because it's not what it's doing. We're going to calculate, and it will depend on the intensity and the wavelength, just as you suspect. Okay, so this, I forget where we started. Were you asking about the tau B?
Yeah.
It's just a model to tell us how short can things be, you know? What are natural time scales? So the atomic physicists, like the one without the 2 pi, and they just call it the natural time scale for electron motion in an atom, just like the Bohr radius. We all use the Bohr radius over and over again, but we're not always talking about hydrogen atoms, especially only in the lowest orbit. So they're just sort of standards of to compare things to. Good enough?
Yeah, thanks.
Or still confusing?
Oh, this is good for me.
Yeah, anyway, those are good questions, both questions. Why? But at any rate, these give us a sense of space and time and electric fields in an atom. They'll be different for different atoms, but it gives us a sense of where we're starting from. What is it? There's something I wanted to say and I can't get it. Yeah, okay, it'll come to me and I'll come back. Oh, here's some of the other equations. So these matter. I don't know if they comes up in the homework problems or not, but if you're working with high harmonics, what really matters is the electric field. You know, that's what leads to electrons being pulled and accelerated and everything else. But we don't measure electric field, we measure intensity. So this is a relationship between the average intensity, this bar means averaged intensity averaged over one cycle, okay? And this is the relationship with the peak electric field. So if you knew the electric field in volts per centimeter, and I think in other places I put it in volts per angstroms or nanometer, but this just this exponent changes, okay? This is a relationship. If you knew the electric field, or if you knew the electric field that you wanted, this would tell you what intensity you need to focus your laser to. So you know your laser has a certain output, and in power, if you had to bring it down to a certain intensity level, what spot size would you need? What kind of lens would you need to do that? This goes the other way. This is if you knew the intensity that you're focused down to, this would give you the electric field, okay? And this X max, this is the calculation someone was just asking about. This is the maximum excursion distance of the electron from the atom. And it depends on the electric field of that incident laser pulse, that focused beam, and it depends on the frequency of the laser or the wavelength squared. So you could just replace here 1 over the lambda squared with the right constants, okay, and see. So for instance, this is a really useful expression then. This is saying, just putting this equation into practical units, it's saying that the maximum excursion is roughly 2 nanometers if your wavelength is 800 nanometers and your intensity is 5 times 10 to the 14th watts per centimeter squared. Your maximum excursion would be 2 nanometers. So we're going to derive this formula, but this is just giving us a view of where we're going. So this, I think, responds to the question of, shouldn't the excursion distance depend on the wavelength and the intensity? Okay, not the wavelength.
Yeah.
Yeah, the electric.
Sorry.
Yeah.
So then from there, would like the time would just be, will it just be 1 over the excursion distance?
What was that again?
So because earlier it was tau b, it was like a lifetime, kind of like how much time it would take. So
No,
would this one be like 1 over?
Let me go backwards. This tau b, this is the time it takes an electron. Let's say one of these, if this was a hydrogen atom, just 1 proton in the nucleus and only 1 electron, this is the time for an electron to make 1 orbit, okay? Just one cycle around the n equals 1 orbit. So this is a time scale, just to give us an idea of electron dynamics times. Is that clear? At least that part?
Oh, okay. So they're not the same. Like,
No.
oh, that's why. Yes, so I thought like tau b was like I thought that was like excursion length that like you would. That's why. Okay, now it makes sense. Okay.
Very good. No, this is perfect that you should ask those questions, because otherwise everything's confused for a while. No, this set of equations is only for a perfect hydrogen atom in the n equals with the single electron in the n equals 1 orbit. These are just properties of that Bohr atom just as a model for us. Okay, these have to do with what kind of energy we can get and how long are the cycles and stuff like that. Okay, so we'll come to them again.
Okay, thank you.
Sure. Okay, so we see these equations. Now, here's what I wrote as 6 steps of the high harmonic generation process. Actually, it's quite famous to talk about the 3 steps, but I wanted to put in a little bit more than the 3 steps to start with. And in a moment, I'll show you what they call the 3-step model, okay? So one is the high electric field of a coherent femtosecond duration, intense laser pulse liberates an electron from the atom. So a high electric field from the focused laser beam of short duration liberates 1 electron from the atom, okay? And we're always going to be talking about inert atoms. Okay, so helium, neon, krypton, argon. And we're just going to be talking about pulling off one electron. Okay, the electron, once it's free, the electron is accelerated in the laser field, first away from, and then in a return towards the parent ion. So like the picture we showed a little while ago. And then the electron recombines with the ion in a very short interaction time and emits high energy photons. Okay. So when it says here the electron recombines, if it recombines, the likelihood of it recombining, we're going to see is a small number. Okay. The process simultaneously involves many electron-ion pairs emitting photons in phase driven by the incident laser pulse. So the incident laser pulse is fully coherent, spatially and temporally coherent, and that gets imparted to these high harmonics that are coming out. So the process is that you've got many atoms in a gas, and you're focusing the laser light onto them. Again, a very short pulse. And this process that we talked about above is happening many times throughout the gas, and they're all emitting photons. And in the forward direction, the electric fields associated with those photons that are giving out all add in phase. So we're going to get an n-squared effect, again, as we've seen in other examples, where capital N is the number of recombination events. So if there's a gazillion atoms that lost an electron and the electron came back and recombined with it, that's what capital N is, okay? And it won't be all of the atoms, because in some cases there won't be an electron pulled out, and in many cases there'll be an electron pulled out, but when it returns, it'll miss the ion. It won't come close enough, okay? But anyway, the important point here was just that there's an n-squared effect. So we'll try and talk about that again later so it becomes clear. The spatial coherence of the incident laser field is effectively transferred or imposed on the emitted high harmonic radiation, which could be in the extreme ultraviolet, or that can also reach into the soft X-ray region, we'll see, okay? And the process occurs symmetrically twice per cycle, because the laser pulse has a peak twice per cycle. It has one going up and one going the other way. So it'll be kicking or pulling, it could pull an electron off in one direction, and a half cycle later, maybe from a different atom, pull off an electron in the other direction, okay? So it happens twice per cycle, and it's symmetric. And what else? And there are well-defined phases in all of this. And because of that, we wind up seeing only odd harmonics. And I have a slide to show you why. Why does that mean we only get odd harmonics? And how might we get even harmonics in case we want them? So does someone want to comment on this?
Hi, Professor. I have a question on step 2.
Sure.
So since number 2. Since
Yeah.
in the laser field, the electron is accelerated and decelerated very quickly, will there be some dipole radiation coming out? Like what we learned in synchrotron radiation, if the electron is accelerating or decelerating?
Boy, that is a really good question. So let's see. Yeah, we always say whenever an electron is accelerated, it radiates. The process here, I don't know how to answer your question exactly, but basically the biggest acceleration, really gigantically, the biggest acceleration is when this electron at very high velocity collides with the parent ion and gets stopped in its tracks. So in the space of a fraction of an atomic distance, that electron gets stopped. So that's where the real acceleration is. So there must be something to your question. What's the acceleration like, for instance, when it's turning around or something like that? It is being accelerated. It's gaining energy as it goes up and comes around. But so there must be radiation associated with that, as your question suggests. But the real strong acceleration that's strong enough to lead to EUV and X-ray photons, that happens just during that collision time. So there's probably a more sophisticated answer to it, but I think that's at least has to be partially the truth. Okay, anything else?
So you've mentioned that we only get the odd harmonics. Is there anything in this description that tells us like which ones we get? Like you talked earlier, like we get multiple high harmonics. Is there anything in this process that tells us like which number of harmonic we get, or is that something we're going to elaborate on further later?
We're going to elaborate further, but if I go back to this equation, whoops, the maximum photon energy we can get is 3.1 times this average kinetic energy gained, okay, plus the ionization potential. So this is an upper limit to what we can get. We could get less than that. Okay, it depends on how much is the electron accelerated. What kind of energy does it return with? That sort of depends on where was it born, quote, born. Where was the birth time? Was it born at the peak of the electric field, or a little bit off to the sides, or what? That'll affect. It will affect its return energy. Okay. So, for instance, what we're going to see in a moment, which threw me when I first heard about high harmonic, if the electron is born at the peak of the pulse, you would think, oh, that's the most likely thing. It's the strongest electric field. It's going to pull the electron off. And when the electron gets off, it's in the strongest part of the electric field. So it's really going to get accelerated and gained energy. But then the field reverses. And this electron is eventually, which is around here, it eventually slows it down till it turns around and it comes back. And if it was born exactly at the peak of the pulse, it returns with exactly zero kinetic energy. It gained nothing. What it gained, it lost. So we're going to see that there's some optimum time of sort of birth of when the electron gets out through the tunneling process. Yeah, great question, thanks. So here's a diagram. A laser pulse, a Ti-sapphire laser, is the most common used. A little bit of work on somewhat longer wavelengths, which we'll speak about probably tomorrow. But anyway, that, and here's a typical pulse duration, 30 femtoseconds, but that can be down to just about 3 femtoseconds, okay? So that laser light is focused, and the focusing strength of the lens is chosen to bring the intensity of this laser light. I don't know what the power is, but whatever it is, combine it with an area, power per unit area will give us intensity. And in this region of in this case, it's a gas jet. It's not always a jet of gas. Sometimes there's other ways of holding the atoms together in a near vacuum situation. But anyway, it focuses the radiation down to an intensity of something like excuse me, 3×10⁻14 watts per centimeter squared. And if you go back to those formulas, that corresponds to an electric field, which is about 1/10 of the binding electric field in the Bohr atom. It might be different in neon or something like that, but at any rate, it's going to be in that ballpark. So you're going to focus down to something of order 3×10⁻14, or a little bit more, it depends. If it's argon, I think that number goes up to 10⁻⁵. We'll see in a moment. So the process again is laser light comes out, focus to a small spot, and in this region is where the high harmonics are generated by many, many atoms that are here. And here is shown that flowing away from the focal spot is the continuation of the laser light. Still most of it is there, only some of it was converted, and the high harmonics, okay? And then there's some sort of filter that blocks the IR, the infrared, the 800 nanometer, and lets the radiation go forward that we want, okay? And you'll see in other diagrams, then there'll probably be a grading or something like that to spread this into different wavelengths or photon energy, okay? And this area here is just enlarged here. So in this case, it was a gas jet. These are the inert atoms down at the bottom. Here's the focused infrared radiation coming in, okay? And here's high harmonics being generated throughout the focal region. So all this other gas is not playing any role. The only thing that matters is the interaction region, this little rectangle or approximate rectangle, where there is both the harmonic radiation, which we're going to see, or which we've already had suggestion is going to be a lot of a cone of radiation of ever shorter wavelengths, and then they both exit. That's what's shown here. And there will be questions about, well, if we'd like to have more EUV photons, what's the proper thickness of this? And so there are several effects that matter here. One is just absorption. The EUV radiation is just prime time for getting absorbed because they have photon energies of, let's say, 30, 50, 70 eV. That's just perfect for absorption by any atom that's there, but more. So you could produce some EUV here, but have it absorbed on the way out. So absorption is a limitation on your distance, so you have to calculate that, knowing your density and everything else. And I think if not Thursday, perhaps the following Tuesday, we'll have a look at those limitations because of absorption. And also, a very interesting one is a phase shift. It turns out that, not turns out, it's just true that the phase velocity of the infrared light, how fast it's moving through this region, there is some phase velocity for 800 nanometers. But the phase velocity for our harmonics, which might be, let's say, 15 nanometers, that is different, okay? And so you have to maintain that what you want is you want the photons created here, the EUV photon created here, to be in phase with the photons created here, so they add in phase. The electric fields need to add in phase. So you need to maintain the phase velocity of the infrared driving laser going through with the phase velocity of the harmonics you're producing. And that also can be a limitation, and there are several effects, but one of them is the infrared laser is its phase velocity is largely that in vacuum. The atoms have a little effect, not so much, but the free electrons have a real effect. So there's a plasma effect here in which the phase velocity of the infrared, it becomes faster depending on the electron density that's produced here, the free electron density. There is a plasma refractive index, and it speeds up the wave. And if it speeds it up too much, then if it gets out in front, let's say we had two wave fronts right here, the infrared coming in and the new harmonics being produced, and they're running together. But if the phase velocity of the infrared is faster, then it's going to be producing radiation here, which is not in phase with what was behind it, what was produced earlier, okay? So you need to worry about matching phase lengths, phase velocities, okay? So we'll talk about that again. I don't think today, probably next lecture, okay? Some question about the diagram or what's going on?
Yeah, is the produced UV strongly angular dependent in the forward direction or in all direction?
What was that again?
Is the produced UV in forward direction only or in all direction?
In all directions, it doesn't, first of all, it gets lost. In all directions, they have random phases depending on the atoms, right? Depending on where the atom was. So if you produced some radiation, let's say right here, that was shooting out in some other direction, let's say out the side, you can find another atom, a half wavelength difference in EUV wavelength, also going out the side. They'll cancel each other. Okay, so this is a common effect in scattering. Like when we talked about why the sky was blue, there's also an effect there where scattering out to the side just cancels. But in the forward direction, they're all in phase. In the forward direction, everything is in phase. Even if there was, let's say, a pi phase shift between the infrared and the EUV, it's the same everywhere. So all of these photons in the forward direction are adding up in phase. That's our n squared effect. Going out in the side direction is not only not n squared, because they're all out of phase. There's no phase consistency in the horizontal direction. But in fact, if the density is high enough, there'll actually be cancellations. You have, pick an atom that's going in one way and then just look in a plane a half wavelength laterally, it will cause cancellation. So it winds up, you don't lose too much radiation going out the side. And so that's also a really great question. And I'm sure, I think the answer I gave is, I know the answer I gave is correct, but something to be swallowed. How, if, for instance, when we talk about lasers in a lecture coming up soon, you have the same effect. When you start up the laser, photons are going in all directions. In the end, you only get photons going in the forward direction. And it's the same cancellation in the lateral direction, adding in phase in the forward direction. So this is a little bit of history and dates. When people were starting, people had learned how to make high peak power lasers. You know, I guess we didn't get there, but we talked about the Nobel Prize for producing very short pulses, and we'll talk about it again. But anyway, now that people had really short pulses, they were focusing them down into, for instance, neon. This is with a neodymium glass laser, so the wavelength is a little longer than 800 nanometer. Pulse duration was a picosecond for this one. And this is showing as they increase the laser intensity, there's a little ionization, a little pulling off of number of ions were collected, but the electrons were being pulled off. Just above 10 to the 14th watts per centimeter squared, there's a little bit, this is in neon, there's a little bit of ionization, okay? And as you increase the intensity, it goes up really, really fast, okay? The number of ions. So, and if you get to higher intensities, you start pulling off even more electrons. So this is neon having lost 1 electron, neon atom having lost 2, etc. Okay. And so this was done by this French group and published in 1992. So they were very interested in looking at what do high intensities do to atoms? How many electrons can they pull off? And what else do they see? And so that, again, was 1992. And then here we are in 1993. Anne Lullier and Balco, the group at Stanford, Macklin, Kmetek, and Gordon, and this German group. The Pfeiffer one comes much later. I only added it because it has such a beautiful spectrum. But this is what the early people saw. And by the way, so this was Anne's, Anne Lullier, who's now at Lund, but she was in France at the time, and she's French. This was her PhD thesis. And they were looking at the radiation that was coming out and was quite surprised to see it came out in all these harmonics. It wasn't obvious that they were going to see harmonics. They were thinking, you know, like if you shine intense laser light on a solid target, for instance, you get this really broad spectrum. You get some spectral spikes where there were resonances and stuff like that. But they weren't expecting to see these high harmonics. And around the same time, the Stanford group also saw the spectrum of high harmonics, and they're both, in both cases, they only see odd harmonics. So that was really interesting. And then here's this third group, okay, where now they're starting to have nicely resolved. And they use harmonic numbers H. So I stopped using the harmonic number n, lowercase n, and you'll see in the slides I'm using H. I think I use a lowercase h for the harmonic number, but you can see the harmonics here are quite high. So if they were starting, like say these at the end here, if they were starting at 800 nanometers and they had the 81st, let's say 80th harmonic, that's like 10 nanometer wavelength. So I rounded off, I estimated there, but you sort of see where you were getting down to 10 nanometers. Well, that's a lot of photon energy. So this became a extremely hot topic early on. And this is just a nice clean spectrum, a more modern spectrum. Okay. And this is even more modern. This is from Elio Champenois, who got his PhD here just, I guess it's probably 3 years ago in AST, and he worked at LBL, that's where his experiments were done. He worked in Oliver's group, and this is some spectrum he saw. And he, by the way, is at Stanford. And by the way, we're gonna finish with the lectures a little bit early, so I'll give you a schedule maybe in next week, because we usually in this class, we usually take 3 lab tours. We go to a synchrotron, the ALS typically. We go to a free electron laser at Stanford, so the whole class goes there. And we go to a high harmonic lab on the Berkeley campus. So we've gone to Steve Leone's lab, and this year we were planning to go to Michael Zurch's lab, but I guess that's not gonna happen. So we'll be a little bit ahead. But anyway, so here's some typical parameters again. Ti-sapphire laser, we often say 800 nanometers. It's quite a broad spectrum, but here it's 780 nanometers with a bandwidth of 45 nanometers. So not quite 1 out of 20. The energy per pulse, this is at 1 kilohertz, but the energy per pulse is 20 millijoules, so it's a lot. And the pulse duration is 27 femtosecond, and it's into a gas of argon atoms at 2 torr, okay? And, oh, it's a 6-meter focus to a gas cell, okay? And the energy per pulse coming out, shown here in the 29th harmonic, and this is the wavelength, so I think if you took this and divided by 29, this is the wavelength that you'd get. There's 3 nanojoules per pulse also in that harmonic, in that particular harmonic. There's a 31st and a 33rd, and they probably have similar energies. But if you're going to use 1 pulse out of the train, you started with 20 millijoules and you've spread it into a lot of harmonics, and you're going to get a few nanojoules per harmonic, okay? And the relative spectral bandwidth here, how is approximately 1 over 145, 150, let's say, okay? And why is that? Well, this H is the harmonic number, N is the number of cycles of the 780 nanometers in a 27 femtosecond pulse. We could divide that out and figure out how many cycles does this correspond to? And I'm guessing it's like 9 cycles, is that right? 10, 11, 12 cycles. And so that's this number. This is the number of cycles in the driving pulse. And H is the harmonic that you're looking at. So if you're looking at the 35th harmonic or something like that. Oh, this is wavelengths. Oh, got myself wrong there. The 29th harmonic, okay? So this would be 29, and this would be whatever we figured the number of cycles of infrared were. Basically, the spectral resolution is something like 1 over Hn. This is the total number of cycles at that harmonic wavelength, right? So if the let's get this number straight. The pulse is 27 femtoseconds, and at this wavelength, 1 cycle is a little bit less than 3 femtoseconds. So this would be like 9 femtoseconds, okay? Maybe 10. Let's say it's 10 cycles. This would correspond, this pulse duration would, so we would say, okay, well, we would think that if there's 10 cycles of infrared going on, the bandwidth is 1 over 10. But that's at the infrared wavelength. Within each of those, within every high harmonic cycle, within each of the 10, there are going to be 29 cycles at this harmonic, 26.9. So the number of cycles for each pulse at this wavelength is going to be this product HN, okay? The factor of a half here is, I would say, arbitrary. This, I think he's telling us, I think Ilios is just telling us that if you measure the width of that, this is about what it comes to. But to first order, you're always going to get a bandwidth like this, and we should each make sure that we believe that. I can stop and make a diagram if you want, but again, for each of the infrared cycles, there's going to be H cycles of that particular harmonic wavelength. So this is, right. So this number here is probably 29 times roughly 10, 290, and he took a half, so 450. Yeah, great, that worked. Okay, any question about that? It's just, so this is our experimental data that we're working from, and would like to know how this is all happening. Okay, so this is what's called the three-step model, okay? And here are the 3 steps. They left out a few of the qualifying pieces of information I gave earlier. One, there's tunneling of a valence electron through the atom's potential barrier, meaning that the nucleus has an electric field and it's keeping things in and defining the orbit, okay? And we're tunneling through that potential barrier, meaning the electric field. There's an electric field holding the atom in, and we're not applying an electric field that's strong enough to just pluck the electron right out, not doing that, but there is a possibility of tunneling through that. That's a quantum mechanical tunneling, and it doesn't happen with every atom, but it happens with enough to make this whole thing work. So step 1 is the tunneling of a valence electron into the continuum. That we call the birth, the time at which that, the instant at which that happens, within the field, the laser field, we call that the time of birth, okay? Once the electron is free of the atom, it finds itself free, but it's in the presence of the laser field, which has pulled it out in the first place, but it's now a free electron in a laser field, and at that point, it gets accelerated away from the atom, away from the ion at that point, and eventually turns around and hopefully recombines. And so that was the second step. First step was getting free. Second step is accelerating in the laser field and coming back. Third is relative recombination with the emission of a photon having an energy equal to the binding energy plus the return kinetic energy. So that's called the 3-step model. Does that balance now with things we've been talking about? Okay. Okay, so now we're going to go through the 3 steps. I'll show a little bit more for the different things, but we start with the tunneling of a bound electron in an intense field. And there's so-called Keldysh parameter, a Russian scientist, and he has this parameter here, and he shows that the tunneling process depends on this. What do I want to say? Oh yeah. And so it depends on the ionization potential. The ionization potential, how many EV does it take to get a valence electron free from the atom? And twice this U sub P, this unfortunate name, which I see here, it's called the ponderomotive potential. What it really is the average kinetic energy of the electron. But there are reasons why it's described as a potential. I've used it myself in the past, but I don't find it a very helpful educational thing, okay? So we'll see in a moment why we'll calculate the kinetic energy of an electron in the field, and we'll take its average, and we'll find out that this is what it is. Okay, so those are the two parameters, and the tunneling occurs for high harmonic tunneling when this number is much less than 1. Okay, that's enough to get some electrons to tunnel through this nuclear binding field. And so there are tons of paper on this because it's not a simple matter. This is a true quantum mechanical calculation. So which paper is this? Oh yeah. So this is showing some of the same kinds of ionization curves that we saw before. The tunneling of ionization of noble gases in a laser field. You may remember in the very introduction, I showed you the Nobel Prize slides for Donna Strickland and her supervisor at the time. And Donna is again here. She was at the University of Rochester where she was a graduate student. Okay, so modest laser intensity produces a single electrons for the process without excessive ionization. Too many free electrons and that plasma effect starts to speed up the phase velocity of the infrared wave, and it gets too far out in front of the harmonics it's producing, so that harmonics in the beginning and harmonics in the end are not in phase with each other. Okay, so you don't want too many plasma electrons. Yeah. Oh, I'm sorry. Here's the comment about the IR phase velocity would be affected. Okay. Okay, and it not only affects the phase velocity, but the incoming, it also causes a negative lens effect. So we'll see all of that later, which lowers the intensity because the radiation starts diverging out. And yeah. So here are some ionization curves. What's the fraction of ionization for neon as a function of intensity? And it has a dependence on the pulse duration. So this is neon at 40, 10, and 2.5 femtosecond pulses. Okay, and these curves were done by Christian Ott. He calculated them. I think he was at Argonne at the time, but now he's at Heidelberg. And so you see that this is a very fast rise. But so for neon, here's 1, 2, 3, let's say 4 or 5 times 10 to the 14th. So this right here would be 5 times 10 to the 14th. And if you had this red 40 femtosecond pulse, again, 1, 2, 3, 4, 5, you'd go up here and you would see that you would have more than 10% of the atoms are ionized. So you might, if you got 40 femtosecond pulses, you might want to get back down here someplace. And then for 10 femtosecond pulses, you have to go out to a little bit higher intensity to get the same number of ionizations. So what would this be? 1, 2, 3, 4, 5, 6 times 10 to the 14. Okay, so that's the neon. Okay, and this is the ionization potential of neon, 21 eV. So we're going to see that later because the outgoing photon depends on the return kinetic energy plus the ionization potential. It's actually falling into a well now. It left a well behind. When it disappeared, it's going to fall in, and there's that extra energy also contributing. So this was neon, and these are the other inert atoms, helium, neon, argon, krypton, and xenon. And for instance, let's look at argon. Argon's got more valence electrons, and so at a lower intensity, closer to 10 to the 14th, you're already getting a high ionization fraction. And by the way, Christian kindly computed all of these beautiful curves just for us. All those curves are in the book, and he just did them for us so that we could see what it looks like for different atoms. So in general, we're going to be talking about intensities in the 10 to the 14th range, not getting up to 10 to the 15th very often. Maybe
Professor?
Yeah.
For these graphs, I'm wondering, like, like below 10 to the 14th or and 10 to the 13th, is that
Yeah.
is it that there's a cutoff, or is that like during it, so
It
a
says
tiny fraction of ionization happening below like 10 to the 14th?
well, it's an exponential process, and so it's this quantum getting through the potential barrier. And so if you're below that, your electric field isn't strong enough to pull the electron through. You know, the wave, there's a finite wavelength here, so there's a tunneling effect. Okay, and you don't need the full electric field to overcome that binding potential, that quantum barrier, really. And what this is saying is if you have a lower intensity, that means a lower electric field, there's not much tunneling going on, and it's getting cut off quite sharply because the tunneling process is an exponential process. Okay, so good question. Did I answer it?
Yeah, you did. Thanks.
No. Good. Okay, thanks. These are further calculations. This is from Robin Santra. And he's also, he's in Germany now at DESY, at the so-called Center for Free Electron Lasers. And he works with Linda Young, many of you may know Linda. She's at Argonne National Lab. She's not the director yet, but just wait. Anyway, these are calculations that Robin did also. And the reason for these is because there are sublevels, and it affects this ionization process is dependent. And so this is showing for different initial, which state they were in. What is valuable here is the probability of a neutral krypton atoms, what is the word? Surviving by the end of a pulse. So this is the probability of surviving for a krypton atom to not get ionized. And so for low enough intensity, it's 100% probability it's not going to get ionized. So it goes along with the previous question. But when you get to the intensity of 10 to the 14th watts per centimeter squared, the electric field is now getting strong enough that with tunneling, it can get through the barrier and an electron can get free, and there's some probability of that, okay? And as you increase the intensity and therefore the electric field, the probability of tunneling increases and the probability of the neutral krypton atom surviving as neutral starts to decrease, okay? And again, these calculations depend on what quantum state it's in. Okay, where are we? So this is step 2. That was step 1, had to do with just the tunneling process through the potential barrier. So here's step 2, which is the acceleration of the electron in the laser field. And the quote, time of birth affects the return energy. So here's an electron. Here's a case where the electron is, quote, born right at the peak of the electric field. So here's the amplitude of the electric field. It's oscillating in time. And if the electron tunneled out just at the peak of the laser field, we'll go through some math probably in the next lecture, but the electron would get a really strong acceleration and get to very high energies, but the field starts to turn around and the electron is slowed, and eventually it turns around and it comes back with zero kinetic energy. So the first time I looked at this, I found it quite puzzling, right? But there's an initial value problem that needs to be solved here, okay? A second case is if the electron is born after the peak of the pulse, just a little bit after it, and this happens, by the way, twice per cycle. So that when the electric field is pointing up, when the electric field is pointing down, if you go just past the peak a little bit, then you get maximum return kinetic energy. So we're going to go through a little bit of math next time, and we'll see. And the best angle in phase is pi over 10. In other words, if this is 2 pi, if this is one cycle is 2 pi, then starting from the peak, just go pi over 10, which is around 18 degrees, and that's when you'll get the maximum return energy. So it means that the electron was born a little after the peak of the pulse and gained energy and lost energy, but when it returned, it had the most, okay? And that happens every time the electric field is just after the maximum electric field in every cycle. So we're going to have 2 emissions per cycle, and they're very symmetric. And this is, by the way, going to determine the fact that we get only odd harmonics, not even harmonics. If, for instance, these were at the peak of the pulse and these were somewhat different, not the same phase position, if there was a difference in that, we would also get even harmonics. But I'll show you a diagram later that explains that. And
Professor?
then, yeah, please.
In scenario A, when there's 0 kinetic energy upon return, so because the electron is born at the peak of the pulse, it's that the phases are exactly sort of canceling each other out. That's why we're not getting kinetic energy?
My knowledge of it is a little bit more kinetic, just F equals ma. If you calculate it, and we will, you'll find out that just for an electron at the peak, it comes back with 0 kinetic energy. I don't have any other interpretation than that.
Oh, okay.
Yeah.
Thanks.
Okay, so then the interesting case is for electrons born just after the peak. They get the maximum. And there are other choices. There could have been electrons that were born a little before this or a little after. They'll also come back with energy, but it won't be the maximum. So they won't contribute to the highest harmonics. The highest harmonics are going to get their energy from electrons that were born just at this time. But there's a lot of atoms there, and they're all being illuminated, irradiated, or illuminated by the same pulse. And so there's going to be a lot of different harmonics produced, but the highest harmonics will only come from this point. And now another interesting case is electrons born before the peak of the pulse, like shown here, just before the peak, etc. They actually never return. They disappear. I mean, they're born. They're in the electric field. They start to turn around to come back, and the electric field changes again, and they disappear. They gain energy again, never to return. So there's all these different possibilities. So we could, I think it might be better to stop here and start with this next time, but let's just look at this one slide. So we're going to have we're going to apply F equals ma, and we're going to calculate what velocity is gained in an oscillating electric field. And we're going to find the velocity and the amplitude. How far does it go before it returns, okay? And we're going to get these equations for the velocity. And the big thing is we're going to apply initial conditions. And what's bothering me right at the moment is, yeah, I'm going to stop here because I want to say a little bit more about this first part, okay? But at any rate, what we'll find out, we're going to solve F equals ma, where the acceleration is due to an applied magnetic field, electric field, okay? And we're going to have initial conditions on when it was born and born with what velocity. We're going to say it's born, they're all born with an initial velocity of 0, but there's a time when they were born on the electric field. And we're going to calculate and find what is the amplitude of oscillation. So this would be the maximum electric excursion distance, okay? And we're going to wind up with this equation, and it has to be solved numerically. But for instance, here's an example we can just look at what is the example without going through it. Atoms are radiated at 5×10⁻14 watts per centimeter squared. So there's an electric field associated with that. And if it's at 800 nanometers, this is that electric field. And there was equations that we're going to develop which give the excursion velocity. And also we will have calculated also the velocity, so we can get the energy and what is the return. And for this example, the return energy will be 60 eV maximum, but it depends on the time of birth and the time of return. Okay, so so in principle, for these conditions, 5×10⁻14, we could get a return energy of 60 eV plus the initial ionization energy for neon. So we could get 60 and 20, we can get 80 eV. So that's what we'll talk about at the next time. We'll go through some examples of this. Does anyone have a question before I shut down the slides and then we can talk further?
Professor?
Yeah.
Can I ask for some clarification on one of the slides where you show that the tunneling probability slide? I forgot which one it
I'm
was.
gonna
It was like
search for
the
it.
equation
Whoops.
gamma k.
This one?
Yeah, that one.
Mhm.
Can you clarify what this gammas of k is?
It's just it's a non-dimensional parameter that Keldysh, when he was looking at these penetrating the barrier, the potential barrier, he did a mathematical analysis. We have a whole bunch of papers, and for instance, one year, one of the students did his presentation on these calculations. But at any rate, Keldysh went through all of the mathematics, the quantum mechanics of an electron tunneling through the barrier set by the nucleus, maybe it's the shielded nucleus because there's a lot of other electrons, but there's an electric field that valence electron feels, and to get through it, it's possible by tunneling. So you know about tunneling of light. You can have light go through, let's say, from one prism to another. If you bring the two prisms close enough, where you would think that the light couldn't get through, but because of the finite wavelength of the light, it reaches out, it sort of tunnels out, but it exponentially reaches through the barrier. And so Keldysh analyzed this, and he found that there was a parameter, this ionization potential divided by twice the ponderomotive potential. And that parameter helped to characterize the tunneling possibilities. So we didn't do that.
Okay.
If you want, I could bring a slide next time which shows the tunneling process. Maybe that would be a good idea.
Yeah, so I guess what I'm confused about is like if this parameter, like say if like higher the gamma means like there's a high probability of electron tunneling, then I'm a little confused because like it looks like this tunneling probability is proportional, like it increases with the ionization potential.
Yeah,
But wouldn't that be like the opposite? Because like if it takes a lot of like if it takes a lot of energy for the electron to be relieved from the atom, wouldn't that like make the tunneling probability lower instead of higher?
Mm-hmm. No, you're asking a really good question, and frankly, I don't remember the answer. I remember this is a confusing topic, and what you're saying is you would think the likelihood of tunneling out would be when the ionization potential wasn't so high.
Yeah.
Yeah, that's exactly.
inverse instead of like kind of
Exactly.
proportional to it.
Yeah. Okay, so I'll try and
But didn't you say we want that gamma to be significantly less than 1?
Yeah.
So isn't that compatible with tunneling happens when that I is smaller? Which
yeah, well, that's a good, Lorena, that's a good point. That we can't have tunneling if we don't have a strong potential. So that's a good point. We need this to be high enough that the electrons aren't just falling off with a small electric field applied to them. Well, let's give it some thought. I'll see what other information I can find on why that's so. But good that everybody's alert. Thank you so much. Anything else? Okay, let's see. Okay, so we're all back. Okay, so I'll see you Thursday, and we'll get into this a little further. And thinking about homeworks again, I don't know if we'll be far enough along on Thursday to make an interesting homework assignment. So we might, let me give it some thought. We might put that off till the following week. Maybe till after we've had a third lecture, okay? Okay, well, look forward to seeing you all Thursday.
Thank you.
Yeah.
Bye.